friends, we have reached the last stage of this course. Today is the last lecture, and I plan to give you current trends in plasma physics and with some concluding remarks. I will discuss nonlinear waves, saturation of instabilities, parametric instabilities, anti-turbulence, laser-driven electron acceleration, laser-driven proton acceleration, laser-driven fusion, and then I will make some concluding remarks. The references would be a classic book by Ginsberg, another one by Kruer, a very famous review article by Nishikawa and Liu on parametric instabilities, then our book on interaction of electromagnetic waves with electron beams in plasmas, and finally a recent paper that we published on laser-driven ion acceleration. Well, you might have recognized that in this course our focus has been on waves and instabilities primarily. Well, we essentially discussed electromagnetic wave propagation in plasmas, electrostatic waves in plasmas, surface waves in plasmas, and then their applications. And we also talked about true stream instability, relative instability, viable instability, and so on. So both kinds of waves we studied, the waves that are damped via collisions or by Landau damping, and also the waves that are driven unstable by free sources of energy, sources of free energy. These are valid only in the linear stage of the instability or when the amplitude of the wave is low. Well, we also discussed in this course some important applications, especially related to magnetic confinement of plasmas, namely the mirror machine and the tokamak. And we spent some time on classical transport also. So the natural corollary would be that the next stage of this study should be essentially nonlinear waves, the waves that have acquired large amplitude, and what way their phase velocity is modified, group velocity is modified in the plasma, or can they be self-focused, or can they travel without distortion via dispersion? So can we compensate for self-distortion of waves by some nonlinear effects, and such waves are known as then solitons. So that is a natural corollary or natural extension of this course to study nonlinear waves. And then also we would like to examine, rather one should really examine in detail the saturation of instabilities, how the instabilities saturate. And in this process of high amplitude wave interaction with plasmas, people discovered that there is a very rich area of plasma physics that talks about wave-wave interaction, nonlinear interaction between waves. Like the phenomena of harmonic generation, phenomena of some frequency generation, phenomena of low frequency generation, and also half harmonic generation or parametric excitation of two waves by a single wave of large amplitude. This is called wave-wave interaction. So a lot of work on this process in this area has been done in last 3-4 decades. And then there is a possibility of wave of large amplitude accelerating charged particles to very high energies. So that gives rise to the phenomenon of electron acceleration and ion acceleration by waves. This is a very rich area of physics with very important applications in even relativity, general theory of relativity, in understanding the evolution of universe, in understanding the radiations coming from pulsars. So very rich physics is revealed by these processes. And then there are some very major applications that have emerged out of high power wave plasma interaction, and one of the major applications is laser driven fusion. We have already discussed the magnetically confined plasmas employed in tokamak and Brer machine for thermonuclear fusion purposes, but there is another scheme that could be realized by high power lasers, is the scheme of laser driven fusion. So today in my concluding lecture I would like to draw your attention to some of these processes. I will discuss some physics of these processes. Let me begin with the fundamental problem of nonlinear wave. Let me begin with the propagation of a high power laser in a plasma. The laser field is like this. This is the direction of propagation of the laser, say z direction. This is the electric field of the laser, or it could be an electromagnetic wave or a radio frequency wave also. Consider the propagation of a wave in a plasma. When the wave acquires large amplitude, well, it will give a large oscillatory velocity to electrons, which we have already learned that this is equal to EEL upon m into I omega, where I am assuming that my laser field goes as some amplitude A exponential minus I omega t minus kz. So this is the linear response of electrons. When we linearize the equation of motion, then we get this sort of velocity. Now what happens if this velocity approaches c, the velocity of light in free space, then the electron mass will get modified. And when we solve the equation a little more carefully, we find that the oscillatory velocity is modified to v is equal to EEL upon m I omega multiplied by the relativistic gamma factor. And this gamma factor turns out to be equal to 1 plus a square by 2 to the power half if the laser is linearly polarized, where a is called the normalized velocity of the electron magnitude, which is EEL upon m omega, same quantity, modulus of this normalized to c. This quantity could be bigger than 1 or comparable to 1, and hence the effective mass of the electron is modified from m by factor gamma, and gamma, if it is larger, then the refractive index of the plasma will be modified, because that depends on the mass of the free electrons. So if I, in view of this, if I write down the effective plasma permittivity, then plasma permittivity at frequency omega is given as 1 minus omega p square by omega square. But now let me write down omega p explicitly, which is 1 minus electron density into E square upon m epsilon 0, this is the value of omega p square into omega square. Here E is the magnitude of electron charge, m is the rest mass of the electron. But now it should be modified because of the gamma factor, Lorentz factor, so put a gamma here. Now this gamma depends on the electric field amplitude, and hence this permittivity becomes a function of electric field. And if you plot E versus gamma, epsilon versus gamma, then if gamma is close to 1, it starts from 1. Rather, let me plot this as a function of laser field amplitude. Laser field amplitude, if I plot, start from very low amplitude and then go on increasing the value. This will start from some small value, because this is 1, so this is the value of epsilon. But as gamma increases or laser amplitude increases, this saturates to this value. This is unity here. So, refractive index of a plasma is an increasing function of electric field, and the kind of fields that you plot here, if you calculate the intensity corresponding to these fields, then this occurs at laser intensity of the order of 10 to the power 18 watt per centimeter square. So, at high intensities, just by the relativistic mass effect, the plasma permittivity becomes a function of intensity. Another important thing occurs. Suppose I am launching a beam, laser beam of this sort of intensity, Gaussian laser beam in a plasma. Then the laser amplitude is large on the axis of the beam and it decreases perpendicular in the perpendicular direction. So, the radiation pressure is more here, less outside, and the plasma experiences a force, electrons experience a force in the radially outward direction, and there is a density depletion. So, the density that appears here can also be modified by this radiation pressure force, which is also called point motive force. And this force, if you calculate for the laser, it turns out to be Fp, time average point motive force, or radiation pressure force, is equal to E grad phi p, and phi p is called the point motive force, and it turns out to be phi p is equal to minus mc square by E into gamma minus 1. Gamma is the same expression that I have written earlier. So, the laser exerts a radial transverse force on the electrons, and the electrons move out. As they move out, they carry the ions also with them if you allow them enough time, and this is we call as the ambipolar diffusion of plasma. So, there is a reduction in density that also brings further enhancement in permittivity. So, permittivity of the plasma is a function of the laser field amplitude by two causes. One is the increase in electron effective mass, and second is the radiation force induced reduction in electron density. Now, let us see the consequence of this. It is a very fascinating consequence. This results in the process of self-focusing. Let me explain the physics. Now, consider a plasma in which a laser beam is traveling. This is the wavefront of the laser beam, and this is the intensity distribution. Normally people take it to be Gaussian laser beam with maximum intensity on the axis and a monotonically decreasing function of transverse distance r. Now, this is called the axial region, where permittivity of the plasma has become larger, and the refractive index is defined as effective plasma permittivity to the power half. Actually, I should use a symbol epsilon effective rather than epsilon, but it is implied, even if I do not use this subscript effective, that this is the effective relative plasma permittivity, and a refractive index of the medium is related to this quantity. So, the plasma, when the laser travels in a plasma, the portion of the wavefront which is near the axis will travel with a lower phase velocity, because phase velocity of the wave is equal to c upon the refractive index, and the marginal rays will travel faster with larger phase velocity. As a result, this wavefront will acquire a curvature, because this travels less distance and this travels more distance, so they will acquire a curvature, and then the waves will converge further in an avalanche manner, and this will reduce to a very small size. This is called the phenomenon of self-focusing. However, when the laser converges, two things happen. The diffraction divergence increases, because when the size of the wavefront is comparable to wavelength, then a strong diffraction divergence occurs. And secondly, as the intensity increases, the permittivity saturates. So, one has to balance these two things, and the laser, after acquiring some minimum spot, starts diverging again. But this is a nonlinear phenomena, nonlinear stage. Beyond this point, Actually, laser acquires some sort of average spot size and continues to travel without convergence or divergence. The important issue is that in a nonlinear medium, in a plasma, at high intensity, the laser has a tendency to self-converge. And this phenomenon is very important because all nonlinear effects depend on the laser intensity. If self-focusing can cause enhancement of intensity of radiation, then the yield of nonlinear phenomena would be very large. One thing more, normally we use lenses to focus radiation. If I shine laser light on a lens, it will converge to a point, and the typical size of this spot is of the order of a laser wavelength. But then the rays come over here and then they diverge like this. So the region where the intensity is large is very small. In a plasma, the region where this laser is focusing then continue to be like this for a very long distance, maybe tens of wavelengths. So the spot size could be quite large, and hence large intensity region of a self-focused laser beam could be much longer than one would realize by using a lens. So it is a very important nonlinear phenomenon, and Akhmanov and co-workers did pioneering work on this. They published a review article in Soviet Species Uspekhi in late 60s, and I think the references that I have mentioned, our book also has utilized their paraxial ray formalism to study this phenomenon. Effect in one dimension due to this nonlinear permittivity is called solitone formation. You know, if I send a pulse which is limited in time, suppose this is my pulse traveling in a medium in z direction, but it is localized in space and time. The laser may be having uniform intensity in the xy plane, but suppose the pulse is of finite duration and limited in space and time and is traveling like this. Then this pulse is equivalent to many frequencies. A pulse of finite time duration is equivalent to a superposition of waves of many frequencies, and a plasma being a dispersive medium, different frequency components travel with different velocities because omega, where the refractive index depends on the frequency. So a wave of finite time domain, finite time period, finite time pulse duration would have a self broadening as it travels because different frequency components travel with different velocities, different phase and group velocities, and consequently this will broaden. Now when the pulse broadens, the intensity falls down. So it is always desirable to counter this effect. We have just seen that the nonlinearity has a tendency to converge energy in the regions of higher intensity. In this case also, nonlinear effects will have a tendency to converge energy from here to here and bring it from here to here, and hence to retain the original shape of the pulse. So if you choose laser intensity of proper value, then the laser pulse you can avoid the pulse distortion. You may counter completely the diffraction, the dispersion broadening. So nonlinear effects can counter dispersion broadening. The mathematical analysis is very similar to self-focusing, and then the pulse will propagate without distortion, and such a pulse shape which propagates without distortion is called solitone. So this is another interesting field. A lot of work in this field has been done. Currently, optical fibers are also using solitones for communication. Well, Another important effect is nonlinear mixing between waves or parametric instabilities. Let me just mention a few words about what is a parametric instability. Suppose I have a large amplitude EM wave or laser. You may take a laser wave or plasma wave or any large amplitude wave. Let me denote this field by E0, amplitude A0, exponential minus I, omega 0 t minus k 0 z. Subscript 0 I am using for the wave of large amplitude. Suppose the wave is traveling in a plasma like this. What can happen? That this wave may couple with a low amplitude wave that may pre-exist in the system, and that low amplitude wave may be suppose a plasma wave. Suppose there exists a plasma wave in the system and the electric field of the plasma wave is minus grad phi, and phi I write down as A exponential minus I omega t minus kz, for instance. Suppose there exists a wave of frequency omega and wave number k in the system and my laser is traveling. What would happen? It is possible that these two can couple. How would they couple? This plasma wave, whenever it travels, will give rise to density perturbation, and if you use cold plasma theory that we did earlier, it turns out to be equal to minus E k square phi upon m omega square. This is the density perturbation caused on electrons, where n0 is the equilibrium, n00 is the equilibrium electron density of the plasma. So this density perturbation is seen by this electromagnetic wave. Now what this electromagnetic wave will do? It will produce an oscillatory velocity to electrons. So if the wave is going like this, the electric field is like this, and it will cause a oscillatory velocity of the electrons called V0. So V0 is produced by this field of the pump wave, which is equal to EE0 upon m I omega 0. What is the consequence? If you calculate the current, which is a product of density and velocity and charge, J is simply charge of the electron into density of the electrons into velocity. What would they do? This n is oscillating with the frequency omega. Electron velocity is oscillating with frequency omega 0. So the product will give rise to quantities that will vary with frequency omega 0 plus omega and omega 0 minus omega. So a system will produce a nonlinear current J at some end difference frequencies, but built in automatically, and they will produce radiation at those frequencies. Obviously, radiation will be of large amplitude if the current that you produce satisfies a proper frequency wave number relationship. Otherwise, this will be a non-resonant driver. So it can be seen, it can be proved that the wave of frequency omega 0 minus omega z can be resonantly driven, and omega 0 plus omega frequency wave is not resonantly driven, so we ignore it. So now look at the process. A large amplitude laser couples with a plasma wave and gives rise to an EM wave of frequency omega 1, for instance, wave number omega 0 minus omega, frequency, and wave number k1, which is equal to k0 minus k. You can visualize this, you can write this in a different manner. H cross omega 0, bring this omega and omega 1 together on one side and multiply by the Planck's constant upon 2 pi. So this is H cross omega plus H cross omega 1. This equation can be written as H cross k0 is equal to H cross k plus H cross K1. What is happening here? You can visualize this process of coupling as if a pump wave of photon H cross omega 0 energy is decaying into two photons, one of energy H cross omega called a plasmon and another photon of energy H cross omega 1. And similarly, the momentum of the photon of the pump wave H cross K0 is splitting into two photon in momenta. This is the momentum given to the momentum of the plasmon, and this is the momentum of the photon which is scattered or generated. So quantum mechanically, this is the energy and momentum conservation equation. Otherwise, they are also known as phase matching conditions. Obviously, each omega and k must satisfy a linear dispersion relation for the wave that we are talking about. Omega 1 k1 will satisfy dispersion relation for an electromagnetic wave. Omega k must satisfy the dispersion relation for a plasma wave. Omega 0 k0 must satisfy the dispersion relation for the pump electromagnetic wave. Now the question arises, what will happen to the plasma wave? Once this omega 1 frequency and k1 wave number wave is generated, then the electric field of this wave will be there in the system, which will, let me write down how much this would be. E1 will be varying now with amplitude A1 exponential minus I omega 1 t minus k1z. What this will do? This wave will also have a magnetic field. From Maxwell's equations, you can show that this is equal to k1 cross E1 upon omega 1. Similarly, the pump wave will also have a magnetic field. So now look at the situation. You are having a pump wave of wave number k0. You are also having a decay wave or a scattered wave of wave number k1. The electric field of this wave is in this direction. This is my E0 and this is my E1. And the magnetic field of this wave will be perpendicular to this plane. Magnetic field of this wave will be perpendicular to this plane. So what will happen? The electrons which were oscillating in the direction of E0, they will see the magnetic field of omega 1 wave and they will experience a Lorentz force, also known as Porndomotive force, and that will be in this direction called Fp. And how much this Fp is, let me just write down. This Porndomotive force is the charge of the electron into velocity of the electron due to the one wave cross magnetic field of the second wave, EM wave. And similarly, you can multiply this V due to the scattered wave and magnetic field due to the first wave. These were the terms that were ignored in the process of linearization when we solved the response of electrons to the EM wave. But now if you retain these neglected terms, they are called the nonlinear force or Porndomotive force, and they give rise to the direction of this force is parallel to z axis, because this is in the x direction, this is the y direction, so x cross y is z. This is a longitudinal force. The force is in the z direction and has a variation also in z direction. Phase variation is in this direction. That is the beauty. So what will this do? This force will cause compression, rarefaction, compression of electrons, rarefaction, compression of electrons. And this will essentially reinforce the original plasma wave or amplify the plasma wave. So this force amplifies the initial plasma wave. So now look at the beautiful process. There was a plasma wave, and you brought in EM pump of frequency omega 0 k0. That produces a current, and that current then produced a omega 1 frequency and k1 wave number EM wave. So, plasma wave generated a electromagnetic wave in the presence of a pump wave, and this again interacted with the pump wave omega 0 k0 wave and generated a plasma wave. So, this is the feedback process. That plasma wave of larger amplitude will produce a EM wave of even larger amplitude, and this EM wave called a scattered wave will again beat with the pump wave and generate a plasma wave of even larger amplitude. So, by this feedback mechanism, both these waves grow in amplitude, the plasma wave and the scattered wave, at the expense of pump energy, and this process is known as stimulated Raman scattering. The coupling could also take place with the ionoacoustic wave. This plasma wave, if were not there, suppose there is a sound wave, even then this process is possible. So, this is a fundamental process in plasmas where a large amplitude wave gives rise to generation of two lower frequency waves. In systems with electron beams, even a more fascinating process takes place. What can happen that the omega 0 k0 frequency wave pump, a large amplitude wave is called pump, can give a quantum of energy h cross omega 0 and can pick, if there is an electron beam in the system, can pick a quantum of energy from the electron beam and can produce radiation of higher frequency, we call as omega 2. And the momentum of this has to be compensated also, h cross k0 plus h cross k is equal to h cross k2. This process in which some momentum has to be brought in from the beam and added to a quantum of momentum with the pump wave photon to produce a photon of higher frequency and higher momentum. This process is known as free electron laser instability. You can convert by this process a laser radiation by employing a counter propagating electron beam. You can produce X-rays. This is my laser. Sorry, yeah, if you are having a counter propagating electron beam, then this produces radiation X-rays. Coherent X-rays will be produced by the coupling between these two. This is a very important scheme, and the frequency of radiation, if you work out little theory for this, the frequency omega 2 turns out to be of the order of 4 gamma 0 square into omega 0, where gamma 0 is the Lorentz factor of the electron beam. Gamma 0 is related to beam velocity by this quantity. Gamma 0 is equal to 1 upon under root of 1 minus V 0 square by C square, where V 0 is the beam velocity. So, you can produce coherent X-rays by this parametric process. Lot of work in last 3-4 decades has gone into parametric interaction between waves. Magnetized plasmas are particularly very rich in wave phenomena, and they can give rise to very useful sorts of instabilities. Some instabilities are very bad because they can remove the energy from the plasma, return back to outside space, but some instabilities are very helpful. Now, a word about electron acceleration. How does a laser accelerate electrons to energies approaching GeV? Well, a simple understanding about wave particle interaction is, and that we have seen when we were discussing the free electron laser or Cherenkov free elandau damping, that the maximum interaction or strongest interaction of particles with waves occurs when the condition omega is equal to k dot v beam. When the velocity of electron v is such that the phase velocity of the wave as seen by a moving electron in this direction, that quantity they are equal, then the electron can resonantly interact with the wave, because the Doppler shifted frequency of the wave becomes 0 for the electron. The thing is that if I have a moving electron going in this direction and I want to accelerate it by a wave, then I need a wave that has a component of electric field in this direction. This is the direction of electron velocity, and I want the electric field also to be in the same direction, or rather opposite direction. So there the force is in the forward direction. If I want to accelerate this electron, I would like the electric field of the wave to be in the opposite direction, and as the electron moves, this field should also move with the same velocity, nearly same velocity. Otherwise, if this is a wave going in this direction with the electric field, for any wave that is traveling in the forward direction, if it is a plasma wave, then the electric field will be in half region, it will be in the backward direction, half will be forward direction, half will be backward direction, half forward direction. And if this entire structure is moving with the same velocity as the electron, then the electron will feel as if the field is always accelerating it. Otherwise, if this starts seeing this phase, then this electron will be retarded. So what you require, that the electric field of the wave should have a component in the direction of electron velocity, and secondly, the phase velocity of this wave should be very close to the velocity of the particle. These two things are required. For electromagnetic waves, you know, in plasmas they have a phase velocity more than c. This condition cannot be satisfied. Moreover, the electric field has no component in the direction of wave propagation. So electromagnetic waves are not of much use as far as acceleration of electrons is concerned. But a plasma wave certainly can satisfy this condition. So the issue is that laser can excite efficiently a plasma wave. So laser, let it excite a plasma wave by some process, and this wave then accelerate electrons. This wave can do this job. How will this laser excite a plasma wave? Just now I discussed the Raman scattering process, in which a large amplitude laser was exciting a plasma wave and a sideband electromagnetic wave. But I am saying here, rather than sending one laser, you may send two lasers. So send two lasers of frequency omega 0 and omega 1. This laser is traveling here, this laser is traveling here, this is with electric field E0, and magnetic field is perpendicular to this page. This is called B0, and this is my second laser of electric field E1, and there is a magnetic field B1 also here. So what will happen? This omega 0 frequency laser will impart a velocity to electrons in the direction of E0, but will beat with B1 through the Lorentz force minus E V0 cross B1 and minus E V1 cross V0, and recognize that the real part of V0 is to be multiplied with the real part of B1. Whenever you are multiplying complex quantities in this fashion, real part of the complex quantity is the actual velocity. Real complex part of this complex B1 is the actual magnetic field. So when you multiply the real quantities, you have to be a little careful, and this gives rise to a force at frequency omega 0 minus omega 1, and its value turns out to be simple. It is simply equal to minus m by 2 gradient of V0 dot V1. And if you calculate the electric field of the plasma wave generated in this process, E of the plasma wave goes as 1 upon 1 minus omega p square by omega square. Obviously, it depends on Fp. This is the kind of electric field that is produced by this longitudinal force, and this can be resonantly enhanced by this quantity whenever omega is close to omega p. So, for omega of the order of omega p, the plasma frequency, the amplitude of the plasma wave generated could be very large. The amplitude of the plasma wave is very large. It could be even larger than the amplitude of lasers that were producing it, much larger. So, you have a system in which a plasma wave is generated by nonlinear mixing of lasers. Professor Liu and Professor Rosenbluth carried pioneering work in this field, and they demonstrated the existence of such a plasma wave, or rather excitation by lasers. Now, the issue is, how will this plasma wave accelerate electrons? That is a simple physics. You can just write down the equation of motion, well, in the form of energy equation for electron. mc square gamma is the energy of an electron moving with the relativistic velocity. Gamma is the Lorentz factor. So, rate of change of this quantity is equal to the electric field of the wave, which is E. I am taking to be in the z direction, multiplied by the work done by velocity. So, if I take my electron motion in the z direction, forget the x and y motions, then this equation can be solved, and rather than solving the evolution of energy as a function of time, people want to understand that in the wave phase, because people write electric field of the plasma wave as amplitude A cos psi, where psi is omega t minus kz, and people can gain lot of insight into energy exchange between electron and wave, especially when omega by k is very close to c, slightly more than c, or slightly less than c, just slightly less than c, maybe 0.99 c or 0.95 c, of that order. What happens that if you solve this equation, which is very simple to solve, rather than solving d dt, you solve the equation for d gamma by d psi and d psi by dt, where psi d psi by dt, if I differentiate the expression for psi, it turns out to be omega minus k Vz, and Vz is related to gamma by this relation c into 1 minus 1 upon gamma square to the power half. So, this equation, which is equal to minus E dot V upon mc square, can be written a gamma versus psi equation, and the solution turns out to have this form: gamma minus omega by kc into gamma square minus 1 to the power half is equal to some normalized amplitude of the plasma wave sin psi plus a constant of integration that depends on the initial conditions. The left hand side, we may note omega by k is slightly less than c, so this quantity is less than 1. Gamma square minus 1 under root is always less than gamma square under root 1. So, this quantity is certainly less than this gamma, and hence this left hand side has is positive definite, and the minimum value of the left hand side is, let me call this as f. So, f minimum value of this left hand side turns out to be equal to 1 minus omega square by k square c square under root. You can just check it. So, this is the left hand side which has a minimum value. Now, the C1 depends on the initial phase and initial energy of the particle, initial phase of the wave that is enters. So suppose there is a plasma here in which a plasma wave exists. This is my plasma wave which is moving in the forward direction, and electrons enter here. I want to accelerate this electron. So depending on at what instant of time I enter the electron in the plasma, into the plasma wave, then C1 will be determined by that. If C1 is less than A prime, then all values of psi will not be permitted, because psi, the phase of the wave can change between 0 and 2 pi. So for half values of psi this will be positive, half psi will be negative. So if C1 is less than A prime plus F minimum, all values of psi are not permissible and particles are trapped in the wave, they can be accelerated. So this equation is very rich in revealing that there are electrons which are trapped in the wave, and if you plot gamma versus psi, you get a lot of insight into particle acceleration. Let me just mention that. Just a simple solution of this equation reveals this equation is like this. This is the equation of a separatrix where C1 I have chosen is equal to normalized wave amplitude plus F minimum, and this I have plotted gamma here, this is psi here, and this is a logarithmic plot. 1 is there, 10 is here, 100 is here, 1000 is there, and so on. This is a logarithmic plot. So the electron which enters a wave somewhere here, as it moves, it can go to the peak. It can gain a huge amount of energy. Gamma, if you multiply by mc square, you will get the energy. So initially the energy, suppose the particle is like 10, gamma is 10, it can acquire a gamma like 1000 when it goes from here to here. So just when the wave travels, the electrons trapped inside the wave can gain huge amount of energy in going from top of this gamma versus psi curve to the top, from bottom to top. And that is the scheme people have employed in last 30 years or so to study electron acceleration. A simple physical picture of the scheme is like this. You choose a gas jet target, a plume comes out from here, this is a gas filled in here, and there is a small nozzle here, gas plume comes out here, you shine laser light here, and you see energetic electrons coming out from there. This is the plasma formed here, a wave is excited in this region, plasma wave. Maybe you can send 2 lasers, they will non-linearly combine with each other to produce a difference frequency plasma wave, and that plasma will accelerate electrons and electrons come out. It is simple physics, simple picture, and this can be done by using tabletop lasers. So that is an interesting scheme. A word about ion acceleration or proton acceleration. Proton acceleration are important for cancer treatment. You know, people are using chemotherapy and radiation therapy, but they have harmful effects on human body. Protons do not have. Even people can use C6 plus ions also for that purpose. So I am talking of laser driven proton acceleration. This physics is also very simple, very interesting. You choose a thin foil of some material, maybe choose a thin foil of say hydrogen. This is hydrogen plasma. What will happen? If you shine laser light on this, actually hydrogen in the foil form is not available, but what happens is that if you take any thin foil of some material, some water vapors are there deposited on this face, and when this is converted into a plasma, you can certainly find a significant number of hydrogen ions or protons in the plasma. They want to accelerate. But for the sake of mathematical simplicity or physical picture, let us consider theoretically a proton foil. People have done experiments with carbon foil, diamond-like carbon foil, and so rather than accelerating protons, they can accelerate C6 plus ions. But now let us see what is the physics. When laser of intensity I0 falls on a foil and gets reflected back, if the foil is become a super dense plasma, over dense plasma, then the forward momentum carried by the laser is I0 by C. Backward momentum it comes is minus I0 by C. So it exerts a force on the foil per unit area 2 I0 by C. So radiation pressure force on the electrons per unit area is 2 I0 by C if it is stationary. But this radiation pressure does not apply on the entire foil, it applies only on the electrons of the foil. So the electrons which were initially filled in the entire foil, they are pushed backwards, and they are pushed backward to a small region here, something like this. So in this small thin region, the electrons are pushed. They cannot be pushed further because the space charge of ions left behind will pull them back. So you choose a thickness of the foil such that the radiation pressure force on electron exactly balances the space charge force due to ions. So what I am looking forward is radiation pressure force on electrons is equal to space charge force on electrons. Due to the ions left behind. And what will happen? Beyond this point, the electrons will not move. Rather, these electrons will pull the ion layer with it. So this whole thing moves as a double layer. Electron layer and ion layer, they form a double layer, and this entire system moves under the radiation pressure force without charge separation. And how much is the delta to be chosen for this? If you work out this equality, then delta turns out to be typically equal to laser wavelength upon 2 pi multiplied by the electron density of the foil without compression, before compression, divided by the critical density multiplied by the laser amplitude A, normalized laser amplitude I wrote down. And typically values of A are like 10 or 100, n upon n critical is also like 100, sorry, this is n critical upon, I am sorry I made a mistake here, this is n critical upon, just a second, let me just see. Yeah, this is n critical upon n E. So what happens? Typically, if I choose A like 100, which corresponds to an intensity of the order of 10 to the power 21 watt per centimeter square, choose electron density in the foil to be about 100 times the critical density, so that this ratio is around unity. Lambda of the laser employed in these experiments is about 1 micron wavelength. So this is like 1/10 micron. So if you choose a foil of about 1/10 micron width, shine laser light of intensity 10 to the power 21 watt per centimeter square, then you can accelerate electrons with the acceleration that we call as g, equivalent g of the order of 10 to the power 23 to 10 to the power 24 meter per second square. Compare this with acceleration due to natural gravity like 10 meter per second or 9.8 meter per second square. So this is huge acceleration that you are really producing here, and people have seen in simulations that this scheme can give rise to 1 GeV ions in a very short distance of about 20-30 micron. Very strong acceleration is possible. So this is a very fascinating field of research. Well, a word about laser driven fusion. Well, I am running out of time, but a word about laser driven fusion. Laser driven fusion is a very fantastic scheme. Well, when we were discussing the magnetic fusion, we discussed that the goal is to achieve for break even n tau the product of density of the plasma multiplied by the confinement time of the plasma to exceed 10 to the power 14 per centimeter cube into second, and electron temperature or ion plasma temperature has to be of the order of 10 keV or more. This is the goal. In case of laser driven fusion, people do not confine plasma by any magnetic field or any external fields. They believe that if I have initially a plasma of radius r0, if you heat the plasma, it will expand with sound velocity and tau will be of the order of r0 by Cs. Cs is the sound speed, which is typically 10 to 7 per second centimeter per second. So if you have r0 small, then tau can be small, but to reach this number 10 to 14, you require density to be quite large. So what people do, you shine laser light from all directions here and here and here. This laser will quickly convert this deuterium tritium fuel into a plasma, but as soon as the plasma is formed, this laser does not penetrate because omega p of the plasma is more than the frequency of the laser. As a result, outside region becomes a plasma and core becomes like this, and outside region is a plasma. This plasma compresses the core and laser is absorbed in the outer region called corona. The issue is that from the corona the heat has to be transported to the core and core has to be heated. So there are some schemes, very fantastic schemes have come up for efficient energy transfer from laser to ions. Yesterday in the last lecture I talked to you about Coulomb explosion, in which lasers can efficiently transfer energy into ions. Here also the same process can be exploited, and this new scheme of laser driven fusion is called fast igniter fusion. And one can achieve very high temperature and one can reach the Lawson criteria I think in near future. So we have seen that there is a lot of fascination in plasma activities, plasma research these days, and the basic physics that we discussed in this course I think should give you a fair analytical ability to handle these fascinating phenomena. It has been wonderful being with you in these lectures. Thank you very much.